So we've talked a lot about what makes one set a subset of another set, or what makes one set not a subset of another set. Let's remind ourselves from back in section 4.1 what it means for two sets to be equal. So we learned that two sets, A and B, are equal if they have the same collection of elements. How do we make that into a more rigorous, usable definition in a proof? What we learned in 4.1 is that saying A equals B is the same as saying that for all x, x is in A if and only if x is in B. And if you recall, what that is saying when you have an if and only if statement like that is you have if x is in A, then x is in B, and if x is in B, then x is in A. Okay, so remember that the elements of a set could actually be sets themselves, and make sure you just use proper notation when keeping track of all of this stuff. So this is back in 4.1, what we talked about in class yesterday. And you might notice that in this definition, there is no universal set mentioned, but it was kind of loosely, informally implied that we were talking about a universal set in the background. And we may have even mentioned that in class. So now that we have the idea of a universal set, we can revisit this same formal definition, except we're just making the observation that it's for all x in the universal set U. Okay, so again, here is the breakdown of what x is in A if and only if x is in B means. Which means if we were going to prove set equality, we would need to prove each of these pieces individually. Another thing to observe is that each of these statements in this AND statement can be rewritten using subset notation. In other words, as we were saying, if x is in A, then x is in B. That's exactly what A is a subset of B means. And then if x is in B, then x is in A. That's exactly what B is a subset of A means. You might see an analogy between the statement here in this box and this statement about equality of numbers. Two numbers are equal if and only if the first one is less than or equal to the second, and the second one is less than or equal to the first. And again, we're talking about real numbers. Later on, we'll talk about other number systems that are not in the real numbers. Okay, so the proof structure we're going to need to show that two sets are equal will involve showing that A is a subset of B and B is a subset of A. What we want to do is use this argument structure to help us with a proof involving sets to show a certain relationship exists between two sets. Again, making observations about these symbols, the is a subset of symbol and the is less than or equal to symbol, there's some common properties, and that's the one common property is called the transitive property, which is summarized in this next theorem. So you have three sets, A, B, and C. If A is a subset of B and B is a subset of C, then A is a subset of C. I want to point out that what we're about to look at is not the proof yet. It's just a discussion. It's a little strategy building that we have to do before we can do a proof like this, if we're doing a proof like this for the very first time. Notice that I have a statement of the form, if something, then something. We're proving an implication. P happens to be an AND statement. So if you really wanted to get technical, you could say something like, if P1 and P2, then Q. How do we prove things directly? How do we do direct proof? We assume true the hypothesis of the if-then statement, and then we show that that somehow leads to the conclusion of that if-then statement. And that's exactly what's mentioned here in this short list. So if I'm assuming A is a subset of B and B is a subset of C, how do I show that A is a subset of C? Well, we know that the definition of that would be for all x in U, if x is in A, then x is in C. So we have to prove that this statement is true using these two assumptions. Notice what we're employing right now is the definition of A is a subset of C. This is helping us see what our goal is. And we're probably going to use the definitions of each of these statements, A is a subset of B and B is a subset of C, to help us get to what we want. Okay? When you're trying to prove something like this, you start with an arbitrary element in the set that you're starting with. So we're starting with x in A, and we're going to have to somehow show that that same x has to be in C. Okay, so let's go right to the proof then and see how exactly that is accomplished. All right, we start by assuming that A is a subset of B and B is a subset of C. We're going to pick an arbitrary element of A, and we're going to call that x. The fact that A is a subset of B is something we're assuming allows us to conclude that x has to also be in B. Similarly, since we assumed B is a subset of C, we combine that with the fact that x is an element of B to conclude that x is an element of C. Which means we started with the assumption x is in A, and we did some work to show that x is an element of C. And because we chose an arbitrary element of A that didn't have any kind of special distinctive properties, it was just a generic element of A, the only thing we knew about it is that it belonged to A. That is covering the universality of the statement. So therefore, A is a subset of C. Important thing to note, which we've said before, is that proofs often rely very much on the definitions involved.